Think about how effortlessly you grasp what's happening when you watch a video. You instantly understand if the camera is, say, smoothly tracking a bird, or maybe shaking wildly, or sweeping across a landscape.
Yeah, for us, it's just second nature.
Yeah.
But for computers, getting them to understand that camera movement is a really significant hurdle.
Right. And it ties back to that fundamental idea, isn't it? The way we move affects what we see, and what we see changes how we move. J.J. Gibson pointed that out.
Exactly. It's this constant interplay. And that's what makes teaching computers about camera motion such a fascinating and important challenge.
Important because?
Well, think about all the modern vision techniques. Structure from motion, building 3D maps from 2D images, or SLAM simultaneous localization and mapping which robots and self-driving cars rely on to navigate.
Okay, yeah. They need to know where they are and where they're going.
Precisely. And both depend heavily on figuring out how the camera or the sensor is moving through the world.
And what about things like video language models? The AI that tries to understand video content.
That too. How can an AI truly understand the story or the action in a video if it doesn't grasp how the viewpoint itself is changing? The camera movement is part of the language.
That's a great point. It's not just technical. Camera movement is storytelling. You think of Hitchcock's dolly zoom.
Oh, yeah, the vertigo effect, where the background warps.
Exactly. The camera physically moves in, the lens zooms out. It creates this specific, unsettling feeling. It's deliberate.
Or Spielberg in Jurassic Park, that slow pan and tilt up to reveal the Brachiosaurus. Pure awe built entirely through camera movement.
And Nolan using that rolling camera in Inception to mess with our sense of gravity.
Powerful stuff. These aren't just random movements. They're directing our emotions, our understanding.
And it's not just cinema, right? You see it in games, too.
Absolutely. Even a simple pedestal up shot, maybe like in Legend of Zelda, when you reach a viewpoint, suddenly gives you that sense of scale. Boom, the world opens up.
And even just selfies. That arc motion we do with our phones to show ourselves and what's around us.
We're all amateur cinematographers now, using camera motion intuitively to frame our own little narratives.
So given how naturally we understand this, and how vital it seems for computers to catch up, well, that brings us to our deep dive today.
Right. We're looking at some really interesting new research trying to tackle this exact problem, helping computers understand camera motion in pretty much any video.
And this research introduces something called CameraBench, a new data set and benchmark.
Exactly. CameraBench. It's essentially a huge collection of internet videos, but the key thing is how they've been annotated.
Okay, annotated how? What's different?
Well, they didn't just slap on simple labels. They developed a whole new system, a taxonomy for describing camera motion. And crucially, they did this with professional cinematographers.
So involving the experts who actually live and breathe this stuff.
Precisely. The people who really understand the art and the technical side of moving a camera purposefully. If you're curious, the project page has all the details laid out.
Okay, let's get into that. What makes CameraBench really stand out? You mentioned this new taxonomy.
Yeah, that's a core contribution. It's a very detailed way to classify camera motion. And what's neat is it considers motion from different viewpoints relative to an object, relative to the ground, or just the camera itself.
Different frames of reference.
Exactly. And they use the real language of filmmaking, proper cinematography terms, things like
ollie for moving the camera body forward or back.
Yeah.
Not just zooming the lens.
Right. Or pedestal for moving straight up or down, truck for moving sideways, and then the rotations, pan, tilt, roll. It's the vocabulary from a film set.
So it adds precision. It avoids vague terms like just moving.
Definitely. And getting this taxonomy right wasn't easy. It was apparently a very iterative process.
How so?
The vision researchers and the cinematographers actually sat down together, watched videos, tried to label them, discussed disagreements. They refined the categories based on real-world examples and that expert feedback loop.
That makes sense.
Yeah.
Because describing motion, even for us, can be tricky sometimes, can't it?
Surprisingly tricky, yeah. One big challenge they highlight is ambiguity without a clear reference frame.
What do you mean?
Okay, so imagine a camera moving forward, but also pointing down slightly. Relative to the ground, the overall motion might feel downward.
Right, like a drone descending towards something.
But from the camera's own perspective, it's performing a dolly-in moving forward along its pointing axis. So how you label it depends on what you're focusing on.
Ah, I see. And we probably naturally interpret that based on the main subject or the action in the scene.
We do. We might say the camera is following the skier downhill, focusing on the subject, even if the camera's physical path is complex.
And there's just using the wrong words.
Yeah, that's a common one they found. People constantly mix up zoom, which is changing the lens focal length, with dolly, which is physically moving the whole camera.
Right. Zoom flattens perspective, dolly changes it. Very different effects.
So just establishing that clear, shared vocabulary based on cinematography practice was a huge first step.
Okay, so they have this detailed taxonomy, but they also know annotation is tricky. How did they actually handle labeling thousands of messy internet videos for CameraBench?
They came up with this rather smart two-step method. Label, then caption.
Label, then caption. How does that work?
First, an annotator looks at a clip. If the camera motion seems clear and consistent, they use the detailed taxonomy to label each specific type of movement, dolly, pan, tilt, etc.
Okay, straightforward enough for simple cases.
But if the motion is more complex, maybe a bit shaky, or combining several movements in a way that's hard to pin down precisely.
Like that drone example, maybe. Forward, down, and a bit sideways all at once.
Exactly. In those ambiguous cases, the annotators only label the aspects they are absolutely confident about. They don't force it into a box it doesn't fit.
That sounds much more realistic. Acknowledging the ambiguity.
Right. And then comes the caption part. For those complex or uncertain movements, they ask the annotator to just write a description in natural language.
Ah, so like the camera sweeps down and left, kind of circling the building.
Precisely. It captures the nuance that the rigid labels might miss. And interestingly, they also prompted annotators to explain why they thought the camera was moving that way.
Oh, getting at the intent. Like, is it following someone? Revealing a landscape, creating a specific feeling.
Exactly that. It adds this whole other layer of semantic understanding beyond just the geometry of the movement.
That seems crucial for really understanding video context.
Right.
Okay, so who did all this careful labeling and captioning, and how did they make sure it was high quality?
This is a really key part of the study. They ran tests with different groups of people doing the annotation, and they found a pretty significant gap in accuracy between novices, just regular folks, and professional cinematographers.
That makes intuitive sense. The pros have a trained eye for this.
Definitely. They were much better, much more consistent at identifying and describing the motions using the taxonomy.
Okay, but you can't realistically hire only seasoned cinematographers to label a massive data set, right? It wouldn't scale.
Exactly the problem. So what they did was develop a really rigorous training and quality control pipeline.
Tell me more about that.
Well, it involved super detailed guidelines, not just text definitions, but video examples for every single motion primitive. Clear do's and don'ts, even examples of tricky edge cases.
So really spelling it out.
Yes. And then potential annotators had to go through this training program. Multiple rounds of tests, practice annotations, and crucially, very specific feedback on their mistakes.
Ah, so they weren't just tested, they were actively taught how to apply the guidelines correctly. They were trained to think more like the experts.
Pretty much. And the results were impressive. They found this training significantly boosted the accuracy for everyone, novices, and even the experts got better. It really helped narrow that initial performance gap.
Wow. So good training can make a big difference.
A huge difference. Only the annotators who passed this intensive training were hired for the main CameraBench annotation task.
And they kept checking the quality.
Continuously. Random checks on the annotations, discussions to resolve any disagreements between annotators to reach a consensus. It sounds like an incredibly thorough process to ensure data quality.
It really does sound like a massive effort. Okay, so they built this high-quality, expertly annotated data set. What did they do with it? How did they test if computers could actually benefit?
They used CameraBench as a benchmark, basically. They tested a whole range of existing computer vision models on it.
Which kinds of models?
Both the sort of classic approaches like structure for motion and SLAM.
The ones focused more on geometry and tracking points.
Exactly. And also the newer big AI models, video language models or VLMs, both the ones that classify things and the ones that can generate text descriptions.
Okay, so testing the old guard and the new wave against this human annotated ground truth. What did they find out?
Well, the traditional SFM and SLAM models, they often struggled, especially on complex videos or videos where there wasn't much parallax.
Parallax, that's the apparent shift of objects when the viewpoint changes, right? Helps judge depth.
Right. If the scene is too far away or the movement is too smooth, there isn't much parallax, and these models get confused about depth and motion. They even had trouble with basic things like telling if the camera was simply moving up or down sometimes.
Huh. So even simple movements could trip them up if the scene conditions weren't ideal.
Yeah, especially in dynamic scenes with lots of moving objects or with smooth camera rolls where the background doesn't change dramatically. The paper has some clear examples of these failures.
So those models are maybe too reliant on stable, textured backgrounds and clear geometric cues.
That seems to be the case. Even the newer learning-based versions of SFMS-LAM, while better, could still get confused, mixing up camera motion with object motion in tricky scenarios. CameraBench really helps pinpoint these weaknesses.
Okay, makes sense. And what about the video language models, the VLMs? How did they fare?
They saw more promise there, particularly with the generative VLMs, the ones that can create text. These seemed better at tasks requiring some reasoning about the video's content, maybe inferring the why behind the camera movement.
Interesting. So the models that handle language seem potentially better suited to the nuances.
That was the hint they got. And that observation really spurred the next phase of their work.
Which was?
To take one of these powerful generative VLMs, they used QuenVLMax and specifically fine-tune it using their new CameraBench dataset.
So teaching the VLM directly using this high-quality motion-focused data.
Exactly. And this is where it gets really compelling. Even though CameraBench isn't enormous by modern AI standards, maybe around 1,400 videos used for this fine-tuning.
Relatively small, yeah.
They saw huge improvements, like a 1 to 2 times performance boost across different camera motion understanding tasks.
Whoa, really? That's a massive jump from a comparatively small specialized data set.
It really is. It underlines the value of that high-quality, expert-driven annotation. So, fine-tuning on this data significantly sharpened the VLM's ability to understand and describe camera movement.
And they showed some cool applications of this improved understanding, didn't they?
Absolutely. Things like motion-augmented captioning. The fine-tuned model could generate much richer video descriptions because it understood the camera work. Instead of just a man walks down the street, it might say, the camera tracks a man walking down the street.
Adding that layer of how it's being filmed.
Precisely. They also saw gains in video question answering. The model got better at answering questions specifically about camera movement, like, is the camera zooming in? Or, what is the camera following?
Which requires understanding those primitives they define.
Exactly. And finally, video text retrieval improved too. The model was better at matching video clips with text descriptions that accurately reflected the camera motion involved.
So better searching and finding videos based on how they were shot, not just what's in them.
Right. All these improvements, documented in the results tables, really highlight that targeted fine-tuning on a dataset like CameraBench can make a real difference. It's not always just about more data, but the right data.
It really drives home that quality and relevance are key, especially for complex tasks like understanding the language of cinematography.
Absolutely. The results across binary classification, VQA, captioning, retrieval, they all point to the power of this focused, expertly annotated dataset.
Okay, so let's try and wrap up the key insights from this deep dive into CameraBench.
Sounds good.
We've seen this new detailed taxonomy for camera motion, built with cinematographers using their precise language. Very important.
Right. And we talked about the challenges, the ambiguity, the misuse of terms, and how their label then caption approach tries to handle that real world complexity.
Then there was the whole annotation process, that big difference between novices and experts. But crucially, how targeted training with good feedback could really lift the quality and bridge that gap.
Yeah, that multi-stage quality control seemed vital for building the dataset reliably.
And using CameraBench to test existing models revealed weaknesses, particularly for traditional SFMS-LAM and complex scenes, and even for standard VLMs.
But then the really exciting part, fine-tuning a generative VLM specifically on CameraBench led to those significant performance boosts.
Showing real potential for improving motion-aware captioning, video Q&A, and retrieval. It really works.
That covers it well. A comprehensive approach from definition to dataset creation to model improvement.
Which leads us to maybe a final thought to leave our listeners with.
Okay.
We started by saying how intuitively we understand camera motion, all the nuances it conveys. As AI gets better at interpreting this visual language, thanks to work like CameraBench, what does that unlock?
That's a big question. What are the broader implications? If AI can understand not just what is happening, but how it's being shown.
Could it lead to fundamentally new ways we interact with video, or even create it? Imagine AI tools that don't just edit clips, but understand the cinematic intent behind the camera's movement.
Yeah, could AI suggest camera movements to enhance a story's emotional impact or automatically generate different cinematic styles for the same scene? It's definitely provocative, opens up a lot of creative possibilities, perhaps.
Fascinating stuff to think about.
Definitely. And if you, the listener,